Hello, everyone. This is Sir Aris. Today, let us talk about the third or lecture or part 6 of our lecture on chapter 3. Uh, the topic is about linear combinations, linear functions, and linear operators. To define linear combination, if you have vectors A and B, linear combination means we have A plus B, where A and B are scalars. Geometrically, that means that if A and B have the same tail and do not lie along a line, then they determine a plane. Linear combinations of A and B then lie in the plane, and every vector in the plane can be written as a linear combination of A and B. Um, could be easily demonstrated if you have, let's say, this is your vector A and this is your vector B. So any random vector, let's say vector along vector C, could be written as a linear combination of A and B, let's say some multiples of A and B, and some multiples of A, and some multiples of B, and some multiples of A. That should give you a number times B plus a number times A. That should give you C, any random vector. So if you have a vector I, x, j, y, k, z with tail at the origin as a linear combination of unit basis vectors I, j, and k. A function is said to be linear if you have a function f of r, um, you replace r by r1 plus r2, it's equal to f of r1 plus f of r2. If you have multiply the argument r by a, then the function of that quantity is just equal to a times the function of r. For example, show that fr equals a dot r. A is this vector, r is this position vector. So um, fr a dot r is equal to axx plus ayy plus azz. Then um, if you replace r here by r1 plus r2, then you have this becomes x1 plus x2 y1 plus y2 z1 plus z2 ay y1 plus y2 plus az z1 plus z2. And this is simply ax x1 plus ay y1 plus az z1 plus ax x2 plus ay y2 plus az z2, or simply f r1 plus f r2. First condition is satisfied. For the second condition, that's also simple. See, far is simply a axx plus a ayy plus a azz, or axx plus ayy plus azz, or a times far. Therefore, or not ar, but f of r. Therefore, f of r with a that the function is a dot r is a linear function. Another example, determine if fr, which is the absolute value of r, is a linear function or not. Let's check. Um, Suppose the second condition far, that's simply a r absolute value. You can always factor out the constant a in the um, absolute value, or the square root, or the distance. Um, a times the distance is just a factored out times the distance of r. which is just AFR. So second condition is applied or it is satisfied. First condition, let's check. F of R, which is absolute value of R, that's simply x squared plus y squared plus z squared, and then you take the square root. F of R1 plus R2 is then equal to, let's say, x1 plus x2 squared plus y1 plus y2 squared plus z1 plus z2 squared. Take the square root. That's it. For FR1, that would be x1 squared plus, or let's write FR1 plus FR2. That would be x1 squared plus y1 squared plus z1 squared. Take the square root. Plus separately square root of x2 plus y2 squared plus z2 squared. And obviously this is not equal to this. So fr1 plus r2 is not equal to fr1 plus fr2. Hence, fr is not a linear function. Generally, if the argument is, or the function itself could be a vector, so in that case we have a linear vector function. There are a lot of examples. For example, fields, if you consider fields such as magnetic field. So if you go from one point to another, the field at one point might be different from the field at another point. There could also be, in physics, there are objects called operators. Let's say an operator O. Suppose we have an operator O. It is linear if it follows these conditions. O operating on an object A plus B is O operating on A plus O operating on B. Also O operating on KA, where K is a number. A and B are also numbers or functions, vectors, and so on. O operating on KA is just equal to K times O operating on A. For example, from calculus, we know that the derivative of fx plus gx with respect to x is just derivative of fx plus derivative of gx. Also, if you multiply fx by a constant k, take the derivative is just k times derivative of fx. So d by dx is a linear operator. Let's consider matrices. If you consider this set of equations, which we can compactly write as xy times this matrix times small letters xy, or we can call this R, this one M, matrix M, and this is column matrix R. For every point xy, these equations give us a point xy. If xy are points in a plane, we are moving it to some other point in the same plane, so we call it a mapping or transformation of the plane into itself. We're moving points around on the same plane, so we are mapping the plane into itself. We say that the matrix M is an operator which maps the plane, this matrix M, into itself. Any matrix can be thought of as an operator on column matrices R. It can be shown that the matrix M is a linear operator. That is actually easy. This is just a matrix. Multiply that to a column R. 1 plus R2, you should get MR1 plus MR2 multiplied by a constant. You should get constant times M times R. The mapping of XY into capital X and Y can be interpreted in two ways. We have one set of coordinate axis, let's call it XY. This is a vertical axis. It's horizontal. Okay, this is the point or the vector R over here. That's R with coordinates X and Y. Okay, now suppose we move that to vector R. Let's say this is a vector R. We can do that by, say, rotating this by an angle theta. Okay, so we now have a new X component, let's say that's capital X, and another Y component, let's call capital Y. Okay, um, we can also have a different interpretation of the mapping. Suppose we have one, or here we have one set of coordinate axis, xy. We can have two. Let's say the first, let's call xy. This is our R. Okay, the coordinates are x and y. But instead of rotating the vector R, we can keep R fixed. We map the points, or this could be any point, into another point in the plane. For this case, we explicitly do the mapping by rotating R. Here we can keep R, let's say, uh, to we transform or map into another vector R prime, but we can keep this R prime fixed. Although we will be able to change the components, we change the components by, instead of, so we don't move the vector R, but to get the mapping, we instead rotate X and Y. And here, instead of rotating counterclockwise, we rotate XY clockwise. So we may have something like this. So let's say we rotate X, this becomes X prime axis, and this becomes a Y prime axis. So basically we're rotating this by the same angle theta, just like here, but we rotate clockwise, or yeah, rotate clockwise. Now this R would now have components X prime. Here you have Y prime. In the second interpretation, we can write here in a compact form this column matrix R prime. This is the same matrix M and the same vector R. Or this may not, this is different from the M that we have here, but they are related. Okay, the R's are the same. Okay, the components, although these two are the same vectors, but we are using different components, so the components here and here are different. We are interested in a transformation called orthogonal transformations, where in this case you have, for the transform vector, x prime squared plus y prime squared equals x squared plus y squared. This says that the length of the vector, okay, the length is not changed by an orthogonal transformation. This matrix M is called an orthogonal matrix. So let us show that the inverse of an orthogonal matrix is equal to its transpose. So we make use of this set of equations. X prime equals ax plus by y prime equals cx plus dy. Okay. Next step, we try to form this left hand side. So x, that's x prime squared plus y prime squared. That would be this ax plus by squared cx plus dy squared. Okay, so this is a squared x squared plus 2abxy plus b squared y squared plus c squared x squared plus 2cdxy plus d squared y squared. Um, Grouping say uh, um, similar terms. So let's say a squared plus here c squared times x squared plus 2 ab plus cd xy plus b squared plus d squared y squared. Okay, and if m is orthogonal, then um, you have x prime squared plus y prime squared equals x squared plus y squared. So in this case, you have a squared plus c squared equals 1. That's 1. Um, ab plus c d equals 0. b squared plus d squared equals 1. Okay. So solving for mt times m, we have mtm equals, so m is a, b, c, d. So the transpose is a, b, c, d. Multiplying the two, you have a squared plus c squared, a, b plus c, d. Okay, a, b plus c, d again, and b squared plus d squared. And a squared plus c squared, that's 1. ab plus cd, it's 0. b squared plus d squared, that's 1. Hence, m and m transpose are inverse of each other. Okay, um, so we write mtm equals I is the inverse, and using the relations that the determinant of mtm is the determinant of mt transpose times the determinant of m, and also the determinant of the transpose is equal to the determinant of m. So we then have, let's say, determinant of mtm, that's determinant of mt, determinant of m. Mt is just equal to the determinant of m, so you have determinant of m squared. Okay, so determinant of m squared equals determinant of MTM is just uh, the identity matrix. I wrote here as 1. And the determinant of identity matrix is 1. So the determinant of m, we take the square root. Okay, the solution is plus and minus of the square root of this, so that's plus and minus 1. So there are two cases when determinant of m is 1 and when the determinant of m is minus 1. When it's 1, it corresponds to a rotation. If it's minus 1, it corresponds to a reflection. Let us consider rotations in 2 dimensions. Suppose we want to rotate a vector um, in the xy plane, a vector r, okay, with components x and y. We want to rotate that to a vector capital letter R with components um, capital letter X, capital letter Y. And if this is just the same vector, then this R here is equal to um, R equals R. Okay. Suppose R here is at uh, at an angle phi counterclockwise relative to X, and R is produced by rotating small letter r by theta. Suppose this is theta. Okay, so small letter x in terms of theta can be written as um, the magnitude of r times cosine of phi, or in terms of the angle phi. Small letter y is r sine of phi. Okay, next let's try to solve for this capital letter x. For the capital letter x, r vector and capital letter R vector have the same magnitude, so we can use r cosine of phi plus theta. So that's r cosine phi cosine theta minus sine phi sine theta. And you may write this as r cosine phi cosine theta minus r sine phi sine theta. Okay, so x, capital letter x is, so r cosine phi is x cosine theta minus small letter y sine of theta. For capital letter y, that's r sine of phi plus theta, or r sine phi cosine theta plus r um, cosine phi sine theta, or y, capital letter y is r sine phi, that's y um, cosine theta plus this is x sine of theta. Okay, in compact form, capital letter x, capital letter y in a column vector. Suppose we want to multiply a matrix by small letter x and small letter y, so that to give you x and y. So this should be cosine theta minus sine theta to give this. In the lower second row here should be sine theta and cosine theta. Okay. Um, we can also have a matrix equation like this using a rotation of the axis. Instead of rotating r by theta counterclockwise, we rotate the axis xy clockwise. So in that case, so you have a coordinate system xy, a vector r, we keep the vector, let's say we have another vector r prime relative to a new coordinate system. So instead of rotating this by theta, we rotate xy coordinate system by theta relative theta clockwise, or opposite in direction as uh, the first type. Okay, so our, let's say this is our new x, so this x prime, and this is the y-axis we call y prime. So instead of here we have components x and y. On the x prime y prime coordinate system, this is x prime, and this one here is our y prime. And it can be shown that x prime and y prime are related to xy by a matrix cosine theta, sine theta, negative sine theta, cosine theta. Take note that this matrix it looks similar to this apart from this negative sign. Basically, we can think of it as we replace theta by the negative of theta. Negative theta replaced here, cosine theta is kept, negative of sine, or sine of negative is the negative of the sine. So this becomes positive sine theta, this becomes negative sine theta. Okay, so again, you have these two are called rotation matrices. Okay, this one is also a rotation matrix. We have two different interpretations. We can rotate the vector by theta, or we keep the vector fixed, um, rotate the coordinate system. So we get these two rotation matrices that are related um, by, so the angle, one is an angle of some value theta. Here we replace the theta with its negative. So that's how these two matrices are connected. So for these two interpretations, we call this transformation active transformation. If you want to easily remember, we actively rotate this R. So we rotate that R to capital letter R. Here, this is called a passive transformation. So we keep R, but we rotate um, the axis or the coordinate system by negative theta. It's called the passive transformation. For example, find what transformation corresponds to each of the following matrices. You have A, B, and C and D. Okay. To determine the type of transformations, um, it would be relevant to determine the determinants. So, for example, the determinant of A. Determinant of A is 1/2 times negative 1. So that's negative 1/2 times negative 1/2 minus square root of 3 over 2 minus square root of 3 over 2. So this would be 1/4 plus 1/4 um, 1/4 plus 3/4. I mean, it's 3. So this is 1, which means that A is a rotation. For B, the determinant of B is negative 1. So it's a reflection. For the determinant of C, that's just the determinant of A times determinant of B, that would be negative 1 or reflection. Similarly, the determinant of D is also negative 1 So it's a reflection. Now we know what kind of transformation they are: rotation, reflection, reflection. So for rotation, we also want to know what is the axis of rotation. So to determine that, we can compare A, which is 1/2 of -1 square root of 3, negative square root of 3 minus 1. Compare that with the rotation matrix cosine theta, sine theta, negative sine theta, cosine theta. Okay, so you have here -1/2. So theta could possibly be in the a negative x direction. So if sine or sine theta is negative square root of 3 over 2, then it could theta is can be found somewhere when we have negative y direction. So if we um, try to visualize it, we can find that theta, the rotation angle, is 240 degrees. Okay, so this is a 240 degrees rotation. To find the for B is a reflection, we want to find the the plane at which um, this B would reflect the um, the plane, okay, the xy plane if we use an xy coordinate system. So for B, which is 1, 0, 0, minus 1, we multiply B with any arbitrary column or vector xy. So you have B times xy, or 1, 0, 0, minus 1 times xy. That would give you x, so x, and minus y, which means that for whatever vector you have, if you multiply B, the reflection matrix, on xy, the y component changes. It means that B reflects through. So this is a reflection through x axis. So if you have here, this is your x-axis, this is your y-axis, whatever point you have, let's say this is xy, okay, if you multiply the reflection matrix to this xy, x is still the same, so it's still right here, but y becomes negative. So basically, this is a reflection plane. Xy gets reflected towards x minus y. So that's what this matrix B do. For C, you have C can be written as, so AB, where A is 1/2, -1, square root of 3, negative square root of 3, -1, and 1, 0, 0, minus 1. Does not equal 1, 0, 0, minus 1. This is simply 1/2. That is here, so -1 minus square root of 3. Multiply -1 here, so negative square root of 3 and 1. Okay, so what we do, we want to find the points x, y on the line through which the plane is reflected. Again, we know this is a reflection matrix because the determinant is -1, We just want to find that line containing points x, y through which the plane is reflected. So to do that, we can multiply c to xy. If xy are are points along this line, it means that um, you apply reflection on but on those points, but those points uh, are located along that line through which the plane is reflected. So whatever you do, they will not never they will not change because they are on the line of reflection. So the answer would also be xy. So c is 1/2 -1 square root of 3 square root of square root of 3 1 times xy. That would be equal to xy. So here you have 1/2 xy multiplied here, that's negative x minus square root of 3y. So negative square root of 3x plus y, that's xy here. Or you have negative 1/2 x minus square root of 3 over 2 y equals x. Or here, the lower row, negative square root of 3 over 2 x plus 1/2 y. This two can simplify to a negative square root of 3 over 2y equals 3 over 2x, or negative square root of 3 over 2x equals 1/2 y. Both of them are just equal to um, the line. So it gives us the line y equals minus square root of 3x. Okay, so vectors along this line are not changed by reflection. Are not changed by reflection. So a plane perpendicular to the xy plane passing through y equals minus square root of 3x is our reflection plane. We can do the same for um, matrix D. Okay. We can also have rotation matrices and reflection matrices in 3 dimensions. So for example, a simple form for rotation matrix is this. This transformation produces a rotation of vectors about the z-axis through angle theta. The matrix for rotation about the y-axis is given by this expression. Example, find the mappings produced by the matrices G and K. If you solve for the determinants, they are both 1, so these are rotations. So our goal now is to find the axis of rotation. For G, by inspection, we find that the vector 1, 0, 1. So if you multiply this by 1, 0, 1, it will be unchanged. So that would be our rotation axis. Next step, now we found the rotation axis for this. Next step is to find what is the angle of rotation. So if you multiply G by itself, you get the identity matrix. It means that um, one or G multiplied to a vector would G multiplied twice to a vector would give back the original vector. So G multiplied once to a vector would only give 1/2 of a full rotation, or 180 degrees. So G is 180 degrees rotation um, about the axis I plus K. For K matrix here, the vector 1 minus 1, 1 is unchanged. So I minus j plus k is the rotation axis. K multiplied 3 times gives us 1 full rotation. So um, 1k is just 120 degrees rotation. Okay, so the rotation I going to minus j going to k going to back to I is a minus 120 degrees rotation about this rotation axis.